All right, here we go.
Roll.
We'll make this quick. Get you going on some stuff. Okay, so I want to just review the stuff where we left off in Algebra 2, right, before we were SBAC testing. So we were talking about what do we do? Remember, our goal here in Unit 5. And we've gotten into the part that's kind of the important part of Unit 5. We've just gotten into that before we took a break to review. So phone should be away.
So I was checking my grades.
Okay, I'll be done here quickly, and then you can check your grades and work. It shouldn't take that long. But so I want you to go, we're going to go hard here for about 15 minutes, and then you'll have a chance to work a little bit, check things out.
All right.
So we're going to break down our discussion of solving polynomial equations into just like 3 parts, right? We're going to look at those that have 2 terms. If we have a polynomial with 2 terms that we're going to solve, then we have a certain strategy. That's what we're working on now. If the polynomial has 3 terms, we have a different strategy, which we already kind of know how to do, but this is a different context, so we'll look at that next. And then if it has 4 terms, we have a strategy for that. Okay? And then we even have some strategies if it has more terms or the other ones don't work, and that's kind of the last thing we talk about this unit. Okay? So for today, 2-term polynomials. To solve 2-term polynomials, we're going to use, and that would be questions like that, or actually, hang on, like that one. It looks like 3 terms, but what's the first thing I would do in this problem for any equation? I want to do what?
Just do each one counts.
What do I want to do? 3, okay, I want to set it equal to 0. So I'd subtract 3 from both sides, and right away you'd see that the 3's would cancel, and I'd end up with negative 16 x to the 4th minus 54x equals 0. We've got 2 terms, right? So solving 2-term polynomials boils down to using these 4 patterns. Remember, I made you a promise here. I'm going to give you this is a huge favor I'm doing you, right? Scott, I want you to put that phone on. So I'm going to let you take a full Algebra 2 test that is nothing more than just memorizing some stuff, not doing algebra at all. So I want you to know, and I've got, so these. Okay, I've got perfect squares and cubes. Remember, you have to know those. Squares up through 15, cubes up through 10. So that's one of the things you got to know on them. Okay. You got to know your binomial factoring patterns, and you've got to know your binomial product expansion patterns. We'll review those here, not today, but very soon. Let's do a rough one. We've done assignments. And so there's very little to actually memorize. This is the equivalent of knowing about 12 state capitals, right? So you're going to get credit for it. So that's pretty good.
That's one less than the original 30.
Or you know all 50.
You already know all
Figure
that?
them out right now. Probably not. What if I did?
Alabama, Alaska.
Well, just states.
Capital.
Okay, I've got a couple short, I've got a bucket on there. Don't let me forget at the end, I'll get those for you. Okay, so here we go. So the 4 binomial factoring patterns. Okay, do you remember the first one? This is a sum of squares. So if I have something squared plus something squared, there is no pattern. Correct.
Thank you.
No pattern.
3 for exclamation points.
Good. So if you have a difference of squares, so something squared minus something squared, remember that pattern?
A plus B times
Very good. You guys are on the ball. A plus B times A minus B. Very good. Now, these are the 2 that were a little bit tougher, right? The sum and difference of cubes. So a difference of cubes, if I have something cubed minus something cubed. Okay, you remember how this one works? This one works where you end up with, you know that the terms you're going to get, you know that you're going to get a small term that's going to be a binomial. I mean a small factor and a big factor, sorry. The small factor has 2 terms, an A and a B. The big factor has an A squared, an AB, and a B squared. And you remember what the sign rule is.
plus.
Okay, now hold on. Whatever is there, if it's a difference of cubes, so if we're factoring A cubed minus B cubed, the first factor is A minus B. then it's gonna alternate, so it's gonna go from minus
Plus
to
and minus.
plus, no, and then the last one
Plus.
is always plus, it never changes, right? Okay, make sense? Okay, so it looks like that, right? And then we follow the same pattern with the sum of cubes, right? If that's a plus, that makes that a minus, and that's always a plus, right? So there's our pattern, it's easy, okay? So let's use those. So what if they tell us to factor something completely? If we're supposed to factor something completely, that means we want to break it apart into as small a factors as possible. So what do we do when we factor? Well, we always want to see if we can factor out a greatest common factor. Here we can't. I don't even have there's no x in this, and there's no numerical coefficient other than 1 here, so there's nothing I could undistribute.
You cube
But-
it this side.
Okay, good, but this does fit one of our patterns, doesn't it? So which pattern could this one possibly fit?
X cubed plus X cubed.
X cubed, well, a cubed plus b cubed, right? Okay, so this would be this is the a cubed plus b cubed pattern, and what was that one again?
A minus B,
A
plus B,
plus b,
and A squared
a squared,
minus AB plus B squared.
there we go, okay? Okay, so for us then, we just have to be able to write this as something cubed plus something cubed. So what's our A?
X.
X, okay? What's our B?
9.
9, okay? And then our answer is really simple. We're just gonna follow the template, right? We have this pattern.
Why would
So
you
we're gonna
want it
get-
in the expanded form? Does that just complicate things?
No, you'll see why, because what if we're solving an equation? We want to be able to break it down to where we can use the zero product property, okay? So we get x plus 9 times x squared minus a times b is just 9x plus b squared is 81, right? So there it's factored. Now, something else we want to remember about this too, though, right? We want to remember that the quadratic trinomial factor that we get is irreducible, right? It's an irreducible factor, and so you're never going to be able to factor it any further, and if you set it equal to 0 and solve to find its zeros, they're always going to have i's in there, always going to be imaginary. Okay? It's an irreducible factor, so we know a couple things about it. We know that you can never factor it further. So no magic numbers will ever work, and it's going to have imaginary zeros every time, okay? All right, so we got that one done. Okay, what about something like this? Let's go back to this one. Okay, so what can we do now? We got this thing into standard form. So our goal then, why do we factor these things? Because we want to be able to break it down into small enough factors so we can set the factors equal to 0 and find all the zeros of the function. Right now, we can't. There's nothing, like, we don't know what the answer to that is, right? If I set that equal to 0, well, it's already set equal to 0, and we don't know what the solutions are. We want to try to break it apart until the factors are either linear, meaning the x's are to the first power, or they're quadratic, where, x is to the second power. Both of those are easy. Solving a linear equation is so simple, right? All you do is isolate x. Very, very simple. How do you solve a quadratic equation? Well, you might be able to factor, you might be able to isolate x maybe, but if all else fails, you can always do what? X equals negative b, right, quadratic formula, right? There's always a method for us to get the zeros from a quadratic equation. So our goal is, we always want to be able to factor these things down to the point where the factors are at least quadratic, if not linear, right? But they can't be bigger than quadratic because we don't know what to do. We can't solve them. There's no magic equation if it's cubic. There is no cubic equation. There actually is one. It's really hard to use. Okay. So what do we do first? First step.
See if you any,
Factor out a negative 2x.
Okay, we could factor out a negative. Can we do better than 2x?
8.
No, I guess it's 2x, that's all we can do. Factor out a negative 2x. Okay, and what does that leave behind if we do that?
8x cubed.
Okay, it's the same thing, when I factor out a negative 2x, it's like dividing by negative 2x, right? Good, so that's gonna give us negative 16 over negative 2 is positive 8, x to the fourth over x is x cubed. Here we get negative 54 over negative 2 is positive 27, and then the x's cancel, right? Okay, good. Okay, so far so good. Now, that's cubic though. I've got to be able to break that down further. Okay, what's the pattern I could maybe use there? What
Oh,
pattern?
you can find the cube root of it, it's simply said, I just said
Okay, but which pattern would it be? So like, it's got a cube in it, doesn't it?
Oh,
So would it be a sum of cubes or a difference of cubes that might be useful? Sum of cubes. Okay, so if we could break this thing down into using the pattern, here, let's do it this way. So we got the pattern. We want to use the pattern a cubed plus b cubed breaks apart into a plus b times a squared minus ab plus b squared, right? Okay, so can we do that? Can we break this up into something cubed plus something cubed? Okay, 2x, right? We know the x is being cubed, but what number will it be? A 2, and then this would be a 3, okay? So, and then out front, don't forget, we've got our negative 2x. Okay, but the purple part here then, that's going to break apart, isn't it? That's going to break apart into, it's going to break apart into a.
Why'd you still put the exponent of, or why'd you still cube the one purple? Why is, like, how is 2x cubed the
Well,
same amount as?
2x quantity cubed means I have to cube the 2 and cube the x. Isn't that what you need to
Okay.
get 8x cubed? Okay, but we have to write it as something cubed. So that's like our a, isn't it? Right? So we've got, that's our a, and that's our b, right? And we're following that pattern right there, aren't we? Okay? So the pattern tells us we're going to break it up into a plus b. So I get 2x plus 3 times a squared. Well, a is 2x, isn't it? Right? So what is 2x squared? 2x quantity squared. 4x squared. Okay, so we end up getting 4x squared minus a times b would be 2x times 3 is 6x. And then b squared is 3 squared plus 9. Everybody see that? Okay, once we get it broken into the a cubed plus b cubed, then we can take advantage of that factoring pattern. And then out in front, we've still got our negative 2x, right? And the whole thing, don't forget, is equal to 0. Okay, now we factored it far enough. Look at our factors. Our factors are linear, x is to the first power, right? Linear, x is to the first power, and quadratic, where x is squared. Okay, that's good. That's as far as we need to go. We can't factor that one anyway, can we? So now we can apply the zero product property and just set our factors equal to 0 and solve those simple mini equations, and those are our answers, right? Those are the zeros of the whole big thing, okay? So what do we get if we do that? So if I set negative 2x equal to 0, what's the answer? What's the solution?
Wow. A, no, 2x.
0.
0.
Wait, we
So
did
there's
all
one.
that just to get
There's
0.
one solution, right? Okay, what if we set this one equal to 0? If I set 2x plus 3 equal to 0, what are the two steps to solve for x?
Minus 3.
And then,
5 by 2.
okay, so doesn't that just give us x equals Negative 3/2. 2 down. How many should we get total?
We,
Fourth degree polynomial, so should get 4 complex zeros, right? And none of those factors have been squared, so none of them count for more than 1, so I got 2 to go. Well, the other 2 are gonna come from here, aren't they, right? So now if I set this guy equal to 0, 4x squared minus 6x plus 9, if I set that equal to 0, I can't factor it, I'm just gonna use the quadratic formula, right? So we get x equals negative b plus or minus the square root of b squared. Well, negative 6 squared is 36 minus 4 times a times c. 4 times 9 is 36 times 4 would be 144. So inside the radical, and on the bottom I'm just getting an 8, right? So inside the radical, if we just look at this in a couple steps, let's go ahead, by the way, and split this up into separate fractions. Okay, so we got a common denominator, but let's split that up. So I'm getting 6/8 plus or minus the square root of 36 minus 144 is 108, negative 108 over 8. What's the negative going to do inside the radical?
Imaginary
We're
numbers.
getting eyes, aren't we? Okay. Now we gotta take the square root of 108 and let's simplify that radical using a factor tree. What are factors of 108?
12 and 9.
Okay, I could do 12 and 9.
69.
Okay, and then the 9's a good one because it breaks down into 3 times 3, so I get a pair of, or a couple of 3s. Remember, couples go out, singles stay in. We're trying to simplify a square root, aren't we? What about the 12?
26.
Okay, but better than that, maybe
4 and 3.
4 and 3.
4 and 3, and that's a good one. So I get a couple of 2s, and I got a single 3, right? So then this whole thing is gonna simplify to, well, that's 3/4, isn't it? This whole thing is gonna simplify to, square root of 108 is gonna be 3 times 2, which is 6, times the square root of 3/8 times I. And then the 6/8 reduces to a 3/4, right? So finally, we get down to our answers. X equals 3/4 plus or minus 3/4 times the square root of 3I, right? So there's my other 2 zeros. I get one for the plus and one for the minus, right? Remember, those come, it's not a surprise, they come as a complex conjugate pair. Remember, we talked earlier about how complex zeros that have i's in them always come in pairs, right? Complex conjugate pairs. There they are. A plus b times I, A minus b times I. Okay? We got it. What was the secret sauce, though? The way we did this is we had to factor it first to get it down to the point where we could have small enough factors that we could set them equal to 0 and solve, right? Using our binomial factoring pattern. Okay, so real quick, how about this guy? What's the only pattern that could possibly fit?
No
It's kind of a
pattern.
tricky one. This is a little tricky.
No pattern.
We could just kind of check them off. Could it work for either of the cube patterns? That doesn't work, because x to the 4th, we can't really write that conveniently as
So
something
no
cubed.
pattern.
Could we write x to the 4th as something squared? What?
X cubed times x, or not cubed, x squared times x squared.
Yeah. Okay, so we could write this, we actually could write this as something squared minus something squared, couldn't we? Well, that's just a 4, obviously, but x squared equals x to the 4th, doesn't it? Right? And so that's just following our pattern. That's just our pattern, a squared minus b squared, which we know that's just a plus b times a minus b, right? So then what's this thing become? This is just going to become a plus b, there's my a, right, that's being squared, there's my b, times a minus b, right? And now those are quadratic. We can set those equal to 0 and solve, can't we? If I set this guy equal to 0, x squared plus 4 equals 0, what are the two steps to solve for x?
Minus 4.
Subtract 4
Imaginary number.
B squared.
and square root it, and I have a negative under the radical, so I'm getting i's, aren't I? I'm going to get x equals plus or minus 2i, two solutions, right? And then if I take this one, x squared minus 4 equals 0, isn't that just going to give me x equals plus or minus 2 when I subtract the 4 and square root?
Yes.
There's my 4 solutions, right? Okay, last one for today. We can do this one, we're good. So what do you think?
I want to set that thing to 0.
Set it to 0. Why don't we set it to 0 by adding that to the other side? How about that?
Because you want it to be positive.
Right.
Makes it
We get
easier.
48 x to the 4th minus 243 equals 0. Okay? Now what?
Let's figure this out.
Anything I could undistribute? Oh, and oh, never mind, we're good.
You would have to give either.
Six doesn't go into 243. Even numbers only divide into even numbers, don't they? Right? But what there is a number that goes into both those. 3. Yeah, how do you know 3 goes into both of those? Well, that doesn't matter. Things that end with 3 don't, that's an accident. But if you add the digits up of a big number, you can see if the result is divisible by 3, then the big number is divisible by 3. 2 plus 4 plus 3 is 9. 3 goes into 9, so it must go into 243. 4 plus 8 is 12. 3 goes into 12. I've only said that about 4 times.
I don't believe
No,
it
you
until
haven't.
now.
Yeah.
I mean, I've heard it, but I
81 and
didn't like
16,
want to believe it.
16 and 81.
Even.
So what do I get? Well, if I just divide each of these by 3,
Does that work for every number?
yeah. No, only, you mean like, does it work for 4s? No, it only works for 3s. And it works, that's not, it does work for 9s too.
Would it work for
What about
12s?
But 9, it does work for 12s.
13s?
There are some patterns that are similar to that, but we're not getting hung up on that right now. So 48x to the 4th divided by 3, if I factor out the 3, I'm left with a 16x to the 4th minus 81. Okay, good. But that's still, look at that, that's a 4th degree factor. I can't stop, I've got to break it down further. What's the only pattern? It's a binomial, right? It's 2 terms. What's the only pattern that could work with that one? Square minus square, right? Difference of squares. So I get 3 times. Can I write this as something squared minus something squared?
Yeah.
What's the first something? Ah, there you go. Because 4 squared is 16 and x squared is x to the 4th. Then over here I get a 9, obviously, right?
Yes.
So then this is going to split apart. This is just our difference of squares pattern. So a squared minus b squared is a squared plus b times a squared minus b, right? Done. Essentially, right now they're quadratic. I got the x squareds, I got the factors down to where they're x squared or smaller, right? So I can set them equal to 0. Well, this one, I can just divide both sides by 3. It's just a constant. That one doesn't give us a solution. But these do. If I set 4x squared plus 9 equal to 0, I get 4x squared equals negative 9.
How come you decide not to use the 3 on this one? I know you just said that,
How can we say it again?
that we don't, we're not gonna multiply by 3.
Okay, so the question is, good question. Everybody with me here? We got like 2 more minutes and we're done, so focus hard for 2 minutes. Put that down. So how can we get rid of the 3? Because it's not a variable, right? What's the rule with an equation? I can always, what can I do to an equation? I can add the same number to both sides, I can subtract the same number from both sides, I can multiply both sides by the same number, or I can divide both sides by the same
So if
number.
you divide it, you're just gonna get that. You can't
Yeah.
divide 0.
0 divided by 3 is what?
0.
0. Yeah, so I can just divide each side by 3 to cancel that. Okay, so if I set this thing equal to 0 and solve, I'm going to divide by 4. And now I'm just going to square root, right? So I'm going to get x equals plus or minus, what's the square root of 9/4? Square root of 9 is? Square root of 4 is? And then an I because of the minus, right? And then over here, I'm going to do the same process. There we go. 4 solutions, right?
Yes.
Okay, easy. Go. You got it.
Oh.